Okay, folks, welcome back to part 5-2. All right, so what we want to do in this video is just talk about this whole process of going from start to finish. Here is a series that has both x and n in it. Tell me where it converges. So in the last video, we talked about the series x to the 3n over n, and we started with knowing that it converges from -1 to 1, tested the endpoints. What we're going to do now is kind of add the layer of finding this -1 to 1 interval. Okay, now, if they ask you to find interval of convergence or ratio, or radius of convergence, there's the word I want. There's only two ways to know that. The first way is that you have a geometric series, in which case, as long as your r is less than, the absolute value of your r is less than 1, you're going to have convergence, right? So if you have a geometric, you just take your common ratio less than 1, that's going to give you your interval of convergence, right? And no, you can't use the endpoints because that would be where it's equal to 1, and we know that's no good, right? So if you have a geometric, your whole interval of convergence and your whole radius of convergence is going to come from just taking your r and forcing it to be between -1 and 1. Okay? Now, if you don't have a geometric, the only other way to answer that question is with the ratio test. Okay. So, you wonder why I love the ratio test so much? Not only is it easy to do and easy to interpret, but it also gives us extra information. Okay. So if your series only has an n in it, the ratio test will tell us whether it converges or not. If it also has an x in it, it will help us find out where it converges, what its interval of convergence is. Okay? And that's where this -1 to 1 came from. It came from running the series through the ratio test. So let's do some problems. Okay, here's our first one. We have the series from 0 to infinity, n x to the n over 10 to the n. So we could write out the first few terms of that series if we wanted to, but we don't need to. Okay. We could think of this as this is n, and then this is x over 10 to the nth. So it's on its way to geometric, but this little n ruins it, right? If this was geometric, we wouldn't have to do the ratio test. Not that we wouldn't want to do it anyway. Right? So we've got this series, and the question is, can x be anything at once? Like, what does x have to be in order for this to converge? Like, I put a 2 in here for x. Will it converge? And what if I put a 20 in for x? Will it converge? The ratio test is going to help us find that answer. Okay, so anytime they ask you for either an interval of convergence or a radius of convergence, we're going to do the ratio test. If you're doing this on an open-ended, make sure you state your test. Okay, so we are going to do the limit as n approaches infinity of my n plus 1th term, so n plus 1, x to the n plus 1 over 10 to the n plus 1 divided by your nth term, so I'm just going to write it as times the reciprocal, right? Now notice here, when I did my plus 1s, the x just is the x, right? The only thing that's being affected here by changing the n to the n plus 1 is the n's, right? The x just stays the same. So just like before, it's going to happen that you have a lot of simplification here, right? The x is still hanging around, but that's okay because stuff is going to simplify just the same way that it did before. So I'm going to take my pieces and kind of lump them with their counterpart from my n plus 1th term to my nth term. So for example, this x to the n plus 1, I'm going to pair with my x to the n. So I have an x to the n plus 1 over x to the n. I'm going to take this 10 to the n plus 1 and pair it with my 10 to the n. So I have a 10 to the n on top. I have a 10 to the n plus 1 on the bottom. And then I'm going to take my n plus 1 and my n and pair them in their own fraction. Now, you're certainly welcome to reduce this just by looking at it from here. I find it helpful to break it up and simplify the kind of chunks one at a time. Okay, so remember the ratio test is absolute value. Remember how I consistently forget to put absolute values on? I always just throw them on at the end. It's That's a bad habit that I have. All right, so I'm doing the limit as n approaches infinity, and I need to simplify these pieces one at a time. So look, I have x to the n plus 1 and x to the n. You can rewrite x to the n plus 1 if you are so inclined as x to the n times x to the 1, in which case your x to the n's cancel. You're just left with an x. Same thing here with 10 to the n. I could rewrite 10 to the n plus 1 as 10 to the n times 10 to the 1. Those guys cancel. I'm left with a 10 in the denominator. And then over here, as n approaches infinity, I can't simplify this, but as n approaches infinity, this 1 doesn't matter, and this piece is going to go to a 1. It doesn't bring anything down here. So look how quickly this whole mess simplified down to something very simple, which is x over 10. So from there, we just say, look, if you do the limit as n approaches infinity, I'm just left, oh wait, I already did the limit here, hold on. I already evaluated the n plus 1 over n as 1 up here, so I'm no longer doing a limit, right? This thing simplifies down to x over 10, the absolute value of x over 10, and here's what I know. If you've used the ratio test, for convergence, we know the ratio test has to come out to less than 1. So look, for convergence, this has to be less than 1. So this quantity has to be less than 1 if you want this thing to converge, because the ratio test says if you put those two terms in the quotient and you push that limit to infinity, as long as your result is less than 1, that's convergence. So what I got is an expression in terms of x. So I'm just going to say, okay, well, I'm going to force that to be less than 1. What x values will make that less than 1? Right? And I think we probably all agree that that would be between negative 10 and 10. Okay. So you could just write, you could just go straight to there, or you could write this as a compound inequality, right? Negative 1 less than x over 10, less than 1, and solve that. Okay. Now look, I don't think this is going to surprise anybody, right? If you put a number bigger than 10 in, put a 12 in here, 15, right? Then you're going to have a 15 over 10 to the n. That is bigger than 1, and your terms are going to constantly get bigger. In order for this to converge, this x here has to be less than 10, because if you put a number like 3 or 4 or 5 in here, then if you put a 5 in here, you're raising 1/2 to the n. So your terms are getting smaller and smaller and smaller, and it won't converge. Okay. The question is, what happens at these ends? Right? If I put a 10 in exactly, will it converge? What if I put a negative 10 in? Okay. So the way I like to do this is I draw myself a little number line that goes from negative 10 to 10. And from my ratio test, I know that in here is absolute convergence. So far, I know for sure that my series converges absolutely between negative 10 and 10, but not including those values. So what I need to do next is go investigate just those particular values. Okay, so if x equals 10, what happens to our series? X equals 10. You have n, 10 to the n over 10 to the n. You end up with this series. You end up with 0 plus 1 plus 2 plus 3 plus 4. And you may very quickly notice that those terms are getting larger. Right? So this diverges by the nth term test. So up here, 10, that has to stay open. I can't use that. If you put a 10 in, it's going to diverge. All right, let's go over here and see what happens with negative 10. Okay, now, if I put in a negative 10, this simplifies down in much the same way, but I'm left with an oscillating 1, right? Because the 10 to the n's are going to cancel, but the 1 to the n doesn't have anywhere to go, the negative 1 to the n. So I have a negative 1 to the n times n. All right, now I need to test this series. So look, first thing you would want to do is test it for absolute convergence, right? So throw the negatives away and see what happens. Well, we already did that, right? If you throw the negatives away, you end up with the series of just n, which is what we just tested over here. So I know it's not going to converge absolutely. The only question is, will it converge if I allow this negative 1 to the n to be there? Will it converge if it's permitted to oscillate, right? So for that, we have to apply the alternating series test. Okay, and in this case, the u sub n is literally just n. So let's do our 3 criteria. Is u sub n always positive? Well, considering that n starts at 0 and goes to infinity, yeah, there's no way n is ever going to be negative. Okay. Is each u sub n bigger than the one that comes after it? So are my terms getting smaller? Well, here's your terms. This is just oscillating them, right? So this series, you put it a 0, a 1, you get negative 1 plus 2 minus 3 plus 4. Your terms aren't getting smaller. It fails. Right? So I don't even have to go to the 3rd criteria. It doesn't meet the 2nd criteria of AST. So we have to say that it diverges at 10, negative 10 as well. So I have to leave this open. Okay. It's a lot of work to find out that we already had it right here, right? I cannot include either of these. So if they say, when does it converge? Absolutely. We're going to say from negative 10 to 10. If they say, when does it converge conditionally? We're going to say, never, nowhere, it doesn't happen, right? If this had come out, if this had passed the alternating series test, we would say that, but it didn't. So then if they ask for an overall interval of convergence, we're going to marry these two, which isn't terribly difficult since this is never, and we just get our general negative 10 to 10. Okay? And so what we are saying is, you may use this Taylor series, it will converge as long as you only use x values between negative 10 and 10. We can see that this series is centered at 0. If you weren't sure where it's centered, you can look at your interval, right? The interval is always going to be symmetrical on either side of the center. So if it goes from negative 10 to 10, it has to be centered at 0. Another way they could ask the same exact question is to ask you for the radius of convergence. If they ask you for the radius, they're just saying, from here out, how far can I go? And that would be 10. Now, fun fact, if all they ask you is for the radius of convergence, you don't have to test the endpoints, right? We could have said it was the radius of convergence was 10 right here. If all they ask for is the radius, they're letting you off the hook on testing the endpoints. They ask for the interval, you have to test the endpoints. Okay. All right, let's do another one. All right, so this is in no way, shape, or form geometric, right? So I know I'm going to have to go to the ratio test. So let's go. In this problem, we get to simplify some factorials, which I think you will find super fun. All right, so my n plus 1th term. I'm going to write, well, here, never mind. 2. I want you to make sure, this one's a little bit tricky notation-wise, because this 2, when you're replacing n plus 1, remember that 2 has to be distributed. Don't just write 2n plus 1. It's not 2n plus 1. It ends up being it ends up being x to the 2n plus 2, because you have to distribute. Okay. Down here, I need n plus 1 factorial, so n plus 1 factorial, and then I have to square that. Okay. Now, over here, I just have n factorial squared over x to the 2n. Okay, so look, I'm going to write n plus 1 factorial squared as n plus 1 factorial n plus 1 factorial. So this is x to the 2n plus 2 over n plus 1 factorial times n plus 1 factorial. And this one is n factorial times n factorial over x to the 2n. And of course, it's still the limit. And of course, it's absolute stinking values. All right, so let's separate these things out a little bit. My x to the 2n plus 2 and my x to the 2n can come together. And then I'm going to break these into two fractions. I'm going to pair an n factorial and an n plus 1 factorial, and then in another fraction I'm going to do the other one, because I think it's easier to look at as far as simplifying these if we look at them one at a time. All right, so when we go to simplify, over here you could rewrite x to the 2n as x to the 2n plus 2 as x to the 2n times x to the second. Right? In which case your x to the 2n's cancel and you just get x squared. When we simplify these factorials, there's a little bit of a trick to this that you need to see. Let's just take a little aside here. It's easier than you think to simplify factorials. So I want you to think about what a factorial is. Okay? For example, if I say to you, tell me 5 factorial, right? You're going to say, well, that's 5 times 4 times 3 times 2 times 1. And if I say, okay, well, give me 6 factorial. That's 6 times 5 times 4 times 3 times 2 times 1. So if I gave you 5 factorial over 6 factorial, you might notice that that is going to simplify like crazy because there's all these common factors, right? Everything from 5 down is going to go away. And I end up just with 1 over 6. So if you think about this in more general terms, this is what I have. I have an n factorial, and then on the bottom I have 1 more than that factorial. Think about what you're going to end up with. N factorial can be expressed as n times all the numbers that came before it. So generically, that would be n minus 1, and then the number before that was n minus 2, and the number before that was n minus 3, and so on and so on and so on. I can do the same thing with n plus 1 factorial. N plus 1, the number that came before that was n, and n minus 1, n minus 2, n minus 3. And hopefully you notice that the same exact thing is happening, right? Up here, it went 5, 4, 3, 2, 1, and then up here it was like 6, and then everything from 5 down canceled. Well, look, I have n and then n plus 1. So n plus 1 is on its own, but everything from n down is going to cancel. And this whole nasty thing is going to simplify to 1 over n plus 1. Now, AP does not expect you to do what I just did. They don't expect you to prove this, right? We all just kind of agree that we understand how factorials get reduced, right? But I do want you, if you're looking at people's solutions going, where the heck did all the factorials go? That's where they went. So this n factorial over n plus 1 factorial simplifies down to 1 over n plus 1. And this one does too. Sometimes you'll see an n plus 2 factorial over n factorial. In that case, you're going to have your n plus 2 and your n plus 1, and then all the things from n down cancel. Okay. Oh. All right. Well, that's fine. Okay. Hope you can back up if you miss that. Let's see. Where was I? I had x squared, right? And then I had 1 over n plus 1, and I had 2 of them, so it was squared. That's where I was. All right, so if we now evaluate this limit, now that we have it all simplified down, what happens is I have an infinity in the denominator, right? So you could think of this too as a fraction x squared over n plus 1 squared. You have an infinity in the denominator and some not infinity up here. Right? This is some finite number, and this is an infinity, and it's squared. Okay? So guess what? This is going to go to 0. Now, last time when we did this, it came out as an expression. It had an x in it. And then we said, okay, that has to be between -1 and 1. Okay. This time, the x is gone. Okay. And I want you to think about what that means. In math, if you're solving an equation, and you come down to something like 3x plus 2 equals 3x minus 7, you very quickly go, wait a minute, that's not true, right? I can take 3x off of both sides. The x's fall out, and I end up with 2 is equal to -7, and I go, no solution. Conversely, I could have 3x plus 2 equals 3x plus 2. I could come down to something like that, at which point, if you kept going, you'd be like, oh, wait, the x fell out of the equation, and I landed on 2 equals 2. Anytime the x falls out of the equation, that is math's way of saying it doesn't matter what x is. If we needed x, it would have stayed. Okay? If x falls out, if x cancels out, if x goes away, that means x doesn't matter. And if x doesn't matter, then all we have to do is look at what's left, just like we did down here. Here, when the x canceled, I was left with something not true. So I said, no solutions. In other words, no matter what x is, this is never going to be true. Over here, when x canceled, I was left with something true. So this is saying, no matter what x is, this is always going to be true. This is all solutions, right? This is two lines that are right on top of each other if you're thinking in terms of system of equations. It's the same concept here for the ratio test. We know that the ratio test tells us that your series will converge if the ratio test result is anything less than 1. Well, x dropped out, so it doesn't matter what x is. Okay? The only question is, when is this less than 1? Yes or no? Okay. 0 is always less than 1. Therefore, the series converges for all x. It's never going to happen that this is bigger than 1. This series is going to converge for all x. And look at it. I don't care how big x gets. You have factorial growth in the denominator, which is monstrous, and it's squared. I don't care what x is. Make x 5,000,006. I don't care. Factorial growth will eventually win, and this thing is going to converge. Anytime you see factorial growth in the denominator, it's probably going to converge, unless, of course, there's also factorial growth in the numerator, right? But if you have something with factorial growth in the denominator, it's going to converge. Okay, so as far as finding an interval of convergence or a radius of convergence here, my interval of convergence is just -infinity to +infinity. Centered at 0, of course, so I could say that my radius of convergence is infinity. This is what your cosine series, your sine series, your e to the x series, this is them, right? You can use them anywhere. Excellent news here, when your radius of convergence is infinity, there's no endpoints to check. Love this, when it comes out to less than 1 automatically when the x drops out. Now, it could also happen that the x drops out and you get like a 2 here, right? Then we would say, this diverges. I don't care what x is, that number in front of me is not less than 1, this diverges, I'm out. Okay. If your x drops out, it's just going to be a clear either it diverges because this isn't less than 1, or it converges because this is less than 1. Okay. And it's going to be for all x. So it's either going to be this thing never converges, or this thing converges everywhere. That would be nice if they gave us one like that. They probably will. Okay, let's look at another one. All right, so here I have x plus 5 to the n. So I'm me, so I am immediately going to go to the ratio test. So I say, okay, n plus 1th term, that's x plus 5 to the n plus 1, divided by my nth term, x plus 5 to the n. That very quickly simplifies to just x plus 5, absolute value. As n approaches infinity, there isn't an n here, they're saying it doesn't matter what n is, this thing is going to come out to the absolute value of x plus 5. So all I have to do for convergence is make sure that x plus 5 is, the absolute value of x plus 5 is less than 1. So for convergence, that means if you take 5 off of, solve your little compound inequality here, x has to be between -6 and -4. So look, it must be centered at -5, right? Here's your radius of convergence is equal to 1. My interval of convergence right now is -6 to 4. The question is, can I include the -4? Can I include the -6? All right, let's start with the -4. So if x is equal to -4, this series turns into 1 to the n. So 1 plus 1 plus 1 plus 1 plus 1. That's going to diverge, right? It's going to diverge by the nth term. I need to go no further. My terms are not approaching 0. So this 4, sorry, it diverges here, this -4. I can't fill that dot in. What about if x equals -6? X equals -6, then I get this series. You may be noticing that when you test these endpoints, the series that result are very similar, right? So this one ended up being 1 to the n, this one is -1 to the n. Usually what ends up happening is on one end you have the positive or the non-alternating version, and on the other end you have an alternating version. Okay, so again, if I took the alternatingness off of this, if I took away its negatives, I already know it's just going to be 1, and that's going to diverge. I already tested that over here. So the only question now is, will it converge if I let it oscillate? In other words, can I get some conditional convergence out of this thing? So the only place to go for that is the alternating series test. Okay. Now, this is a little bit of a weird one, right? So this is a -1 to the n. That's your oscillating part, or your alternating part, I should say. But what's my u sub n? Like, literally your u sub n is just a 1. There's nothing else to the series. So my u sub n is 1. You pretty much can tell what's going to happen here, right? So first question, is u sub n always positive? Yeah. Okay. It's 1. Is u sub n always bigger than u sub n plus 1? Are the terms getting smaller? Again, doesn't work. Okay. And then my last criteria here would be if the limit is approaching 0, and that's also a no. Okay. So at this endpoint as well, it's going to diverge. So I have to leave this opened. So once again, all that work, and we don't get to include either endpoint. Sorry. So where's the interval of convergence? Is -6 to -4. It converges absolutely on -6 to 4. It never converges conditionally. It doesn't happen. Okay. Want to do one more? Me too. Oh, this is a good one. Look at all those parts. Yowza. All right. I smell a ratio test. Fantastic. All right. Okay, n plus 1th term. I'm just going to take all these n's, replace them with n plus 1s. Algebra might get a little interesting here. All right, let's see. We have n plus 1. We have x to the n plus 1. Downstairs, we have 4 to the n plus 1. And then this guy, you have to do n plus 1 squared plus 1. So that's n squared plus 2n plus 1 plus 1. So this is n squared plus 2n plus 2. That's my n plus 1th term. Here comes my nth term. Luckily, I don't have to do anything. All right. This is going to simplify like crazy, right? We know this is going to simplify like crazy. Don't play with me, computer. Not today. All right, let's take our pieces and pair them up. Okay, so I have an x to the n plus 1 here, and I have an x to the n here. I have a 4 to the n plus 1 and a 4 to the n. Okay. And then last but not least, I have these polynomial pieces, right? All these n pieces. Right? So I'm going to put them in one fraction together. So I have an n plus 1 times an n squared plus 1. In the denominator, I have n squared plus 2n plus 2 times n. Okay. So this is going to simplify down quite nicely. So check this out. Again, this could be written as x to the n times x to the 1. Your x to the n's cancel, you're just left with an x. This could be written as 4 to the n times 4 to the 1. 4 to the n's cancel, you're left with a 4 in the denominator. Okay. This mess, remember, I'm approaching infinity. I have polynomial over polynomial. So the only thing I care about is the order of those polynomials. If you remember, we did that shortcut at the beginning of the year. It was like, listen, if all you have is 2 polynomials and a quotient and you're going to infinity, the only thing that matters is the end behavior, right? This is a cubic. And if you FOIL this out, this is a cubic. They have the same exact end behavior. This is going to cancel. This whole thing is going to 1. So allow me to go sneak my absolute values back in. I now have the limit as n approaches infinity of x over 4, which, since n is no longer in the expression, is just x over 4, absolute value. So I know that x over 4 has to be between -1 and 1 for convergence. Absolute convergence, even. So that means -4 to 4. Okay, so I'm going to draw my little... I don't know what's going on here, but I know in here I have absolute convergence. So let's test those endpoints, shall we? Okay, I like to start with the one that isn't going to give me an alternating series. So I'm going to start with 4. Okay, if x equals 4, let's see what happens to our series. I'm going to scooch my floating head over. All right, so if x equals 4, oops, sorry, my series is going to turn into n times 4 to the n over 4 to the n, n squared plus 1. These cancel, and I end up with just n over n squared plus 1. Okay, so if I write out the first couple terms of that series, at 1, it's going to give me 1/2. At 2, it's going to give me 2/5. At 3, it's going to give me 3/10. At 4, it's going to give me 4/17, and so on and so on and so on. Okay, so I need to decide if this is going to converge or diverge. Now, it looks to me like my terms are getting smaller, right? This is 0.5, 0.4, 0.3 repeating. I don't know what this is, but something less than 1/4, right? It's got to be less than 1/4. So I'm trying to think of what I can compare this to. So I look up here and I say, look, if I took this plus 1 out of here, this would very quickly reduce to 1 over n. So I'm going to try to compare this to 1 over n, because I know 1 over n diverges, right? So 1 over n is going to give me the series, the terms 1 plus 1/2 plus 1/3 plus 1/5 plus 1/6, blah, 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 blah. So look, 1 over n diverges. So what I need to prove is that my terms here are bigger than the terms here, because the terms are either bigger than or the same as, right? Because if this is diverging, if I can show that these terms are bigger, then it obviously is diverging, right? So look, taking the 1 out of it, because we'll just take our answer and add a +1. Look at your terms. 1/2 is the same as 1/2. 2/5 is 0.4. That's bigger than 0.3 repeating. 3/10 is 0.3 repeating. That's bigger than 0.2. Okay. Your terms, look, this has to be something smaller than 1/4, and I'm going to be comparing it to 1/6. These terms are all going to be bigger than these terms, with the exception of this one sticking out here. But remember, all I need to prove is that all of my terms are going to be bigger than their kind of counterparts down here. So if this guy is diverging, if he's approaching infinity, this guy is approaching infinity as well. So we can say that he diverges. Right here. So at 4, I have to say it diverges. I cannot include that in my interval. All right, so let's check out -4. If you do -4, you have n, -4 to the n over 4 to the n squared plus 1. Now, look, this is what I meant when I said I do the positive one first, right? When I plugged in 4, I got this. When I plug in -4, the only difference is my 4 to the n's are still going to cancel. I just get left with this -1 to the n on top of it. Again, look. I've already proven what happens if I take away the -1 to the n, right? If I take away the -1 to the n, I've got this. I've already proven that diverges, so I don't have to do it again. All I have to do over here is decide, what if we leave the -1 to the n in? Then will it converge? So let's take a look. Alternating series test is the only one we can ask. So my u sub n here is n over n squared plus 1. So let's go with our criteria. Is u sub n positive? Well, n starts at 1 and goes up, so heck yeah, there's no possible way that's going to be negative. Okay. Is each u sub n bigger than the guy that comes after him, right? Are the terms getting smaller? Well, look at the terms of our series, right? 0.4, 0.3 repeating, something less than 0.25. Yeah, they're getting smaller. Okay. And then last but not least is the limit as n approaches infinity of this thing going to 0. Look, first order on top, second order on the bottom, that's going to 0. Check. This thing passes the alternating series test. It fails if you take away its alternatingness, but if you let it alternate, it will converge. Okay. So over here at x equals -4, we have conditional convergence. It's saying, I will converge, but on one condition. You have to let me keep my negatives. Okay. So that means that over here on our interval of convergence, we can include the -4. Finally, we get to include an endpoint. So look, if they ask us our 3 questions about where this converges. What? Oh, technology today. If they ask us where this thing converges, look. They say, where does it converge? Absolutely. We say from -4 to 4, right? That's what the ratio test gave us. Where does it converge conditionally? That would be only at 4, or -4, right? So only at x equals -4. So therefore, our overall interval of convergence goes including -4 up to 4, but don't include it. right? I'm literally taking these two intervals and marrying them. I'm saying, look, it will converge absolutely here. It will converge conditionally here. So overall, where will it converge in any way? Would be -4 to 4, including the -4. So sometimes when they ask that question, I remember when I was first learning this, thinking that they were just asking the same question over and over and over again. I was like, why are they asking me the same question? They're not, right? They want to know specifically absolute. The interval of absolute convergence is what the ratio test gives you. When you're testing those endpoints, you're testing for conditional convergence. Okay? All right, we can do some more practice with this. There's a link to some practice that I'll send you. This is a pretty common question, either interval of convergence or radius of convergence. Again, if they ask for radius, they're saving you, finding endpoints, which is nice, but we never know what they're going to ask. So, all right, questions in the end of the video? We're almost done. Okay, see you soon.